Good morning all. In today's topic we are going to see in unit 3 of vector calculus and complex variable analytic function. So here is some properties of analytic function given. So first Laplacian operator. Tau square divided by tau x square plus tau square by tau y square is called the Laplacian operator and it is denoted by del square. If it is analytic function, it should satisfy the Laplacian operator, either del square u equal to 0 and del square v is equal to 0. Next, Laplace equations. Equation is nothing but it should have both left hand side and right hand side. So tau square psi divided by tau x square plus tau square psi by tau square y divided by tau y square is equal to 0 is known as the Laplace equation in 2 dimensions. So here are some problems given based on the properties of analytic function. First of all, our first sum is check whether x y square is a real part of an analytic function. So in our given question they asked for real part. So if it is a real part, we take the given equation as u. If it is imaginary part, we can take the given question as b. So let u is equal to x y square. Here we have to prove the function, the given function is analytic function, which means we have to prove uxx plus uyy is equal to 0. If suppose if they are asking for imaginary function is analytic, we have to prove vxx plus vyy is equal to 0. Here they are asking for real part, so we need to find uxx and uyy. First of all, we differentiate u with respect to x, so x will become 1, so we get y square. If we further differentiate this u with respect to x, we get uxx, so there is no x in there, so it will become 0. Next, we have to prove uyy. First differentiate u with respect to y, we get 2xy. Further differentiate uyy, we get 2x. We have to add both the things, that is uxx plus uyy, we get 0 plus 2x, which is 2x, which is not equal to 0. So therefore the given function is not analytic function. If the given function is analytic, we should have uxx plus uyy is equal to 0, but in our answer it is not equal to 0, therefore it is not analytic. Our second sum is there is a function given as 2x of 1 minus y can be the imaginary part of an analytic function. We have to show that. So this is asked for imaginary functions, so we can take the given function as b. So first differentiate b with respect to x, we get 2 of 1 minus y. Further differentiate with respect to x, we get 0 because there is no x in the right hand side of vx. Next, differentiate v with respect to y, we get 1 minus 1 inside the bracket, so it will become 0. Further differentiate it with respect to y, we get 0. If we need to add both the thing, that is vxx plus vyy, so both are 0, so we get the answer as 0. Therefore v satisfies the Laplace equation, so we can easily say that the given function is an analytic function. So we saw the analytic function for the real part and also for the imaginary part. Okay, next, the third question. Check whether the function e power minus 2x cos 2y can be the real or imaginary part of an analytic function. So we need to check the given function is real part or imaginary part. So we can take the function as f of x comma y. So e power minus 2x cos 2y. First of all, we need to differentiate f with respect to x. We get the exponential e power minus 2x will become minus 2 into e power minus 2x. So there is no change in cos 2y. So keep as it is. Further differentiate this x with respect to x. We get further minus 2 into minus 2. It will become 4 e power minus 2x into cos 2y, because the function cos 2y is in y, so there is no change in that. Next, we have to differentiate the function with respect to y, so keep the exponential term as it is, that is e power minus 2x as it is. So cos 2y, if we differentiate this cos 2y with respect to y, we get 2 sin 2y. So further differentiate this with respect to y, we get minus 4 e power minus 2x into cos 2y. Add both fxx plus fyy, we get 4 e power minus 2x into cos 2y minus 4 e power minus 2x cos 2y. So one in plus term and another in minus term, so both will cancel out each other. So our answer is 0. Therefore f can be either real or imaginary part of an analytic function because it is both in x and y, so it can be both real or imaginary part. So next sum, fourth sum, the given function is e power ez, then show that u and v are harmonic function. Harmonic function is same as analytic function. We need to prove that uxx plus uyy equal to 0 and also vxx plus vyy equal to 0. If both the terms are satisfied, which means the given function is an harmonic function. First of all, take the given function f of z is equal to e power z. We can substitute for z as x plus iy. Separate both the term, that is e power x into e power iy. We know the value for e power I theta, that is cos theta plus I sin theta. Substitute it, so we get e power x into cos y plus I sin y. Multiply this e power x inside the bracket, we get e power x cos y plus I e power x sin y. So here is the function. We have to solve this for u and v. So take the real part as u and imaginary part as v. Here the real part is e power x cos y and the imaginary part is e power x sin y. So we need to show uxx plus uyy equal to 0. So we have to differentiate this u with respect to x. So e power x will become as it is e power x into cos y. Further differentiate this with respect to x. We get uxx. So e power x is same as it is e power x into cos y. Next, differentiate u with respect to y. There is no change in e power x. So cos y. If we differentiate cos, we get sin. So cos y will become sin y. Further differentiate this uy with respect to y. We get e power minus x into sin will become minus cos. So minus cos y. Next, our imaginary term v is equal to e power x sin y. Differentiate with respect to x, we get e power x sin y. Further x, we get same e power x into sin y. Differentiate v with respect to y, sin will become cos. So e power x into cos y. Differentiate vy with respect to y, we get cos. If we differentiate cos, we get minus sin. So e power x into sin y. So first we have to add uxx plus uyy. So first uxx is e power x cos y and uyy term is minus e power x cos y. Both cancel out each other. So we get the answer as 0. Second, vxx plus vyy. So vxx value is e power x cos y and vyy value is minus e power x sin y. So both cancel out each other. We get the value as 0. So both satisfy the analytic function. Therefore, we can easily say that the given function is an harmonic function. So see, second order partial derivative of u and v are continuous. So u and v are harmonic function. Okay, one more question. Show that the function u is equal to 1 by 2 log of x square plus y square is harmonic. Similarly, we have to prove that uxx plus uyy is equal to 0 because they are asking for the function only for u. So we need only to prove that uxx plus uyy equal to 0. If the function is given in v term, means we need to prove vxx plus vyy is equal to 0. Or simply if they are asking for harmonic, means we need to prove for both real and imaginary term, that is u and v. So take the given function u is equal to 1 by 2 log of x square plus y square. So we need to prove for uxx and also for uyy. So first differentiate this u with respect to x. So 1 by 2 is constant, keep as it is. Log z, if we differentiate log z, we get 1 by z. So here the given term is log of x square plus y square. So it can be written as 1 divided by x square plus y square. The given function is differentiate with respect to x. So we can easily write 2x. So cancel out 2 and 2 in both numerator and denominator, and the remaining term is x divided by x square plus y square. Next, we need to differentiate this ux with respect to x so that we get uxx. See, ux is given in u by v format. We know the u by v formula. So differentiation of u by v is nothing but vu dash minus uv dash divided by v square. So that is x square plus y square. If we differentiate u with respect to x, we get value 1. Next, keep u term as it is. So minus x, differentiate v with respect to x, we get 2x divided by v the whole square, that is x square plus y square the whole square. So multiply this 2 inside, so 2 into 2 4, so x square plus y square minus 2x square divided by denominator as it is. Here there is 1x square and also minus 2x square. Simplify it, we get y square minus x square divided by x square plus y square the whole square. Next we need to prove for uyy. So differentiate our given function u with respect to y, we get y divided by x square plus y square. Further differentiate this uy with respect to y, we get the value x square minus y square divided by x square plus y square the whole square. Same, this is also in u by v format. We can use the formula and simplify it, we get the answer. Now we have to add both uxx and uyy. See, in uxx the term it is in y square plus minus square, y square minus x square. Here in uyy, x square minus y square. So both x square minus x square, y square minus y square cancel out each other, we get the answer as 0. Since the equation satisfies the analytic function, we can easily say that the given function is the Laplace equation, therefore u is harmonic. Okay, our next sum is, if f of z is equal to u plus iv is a regular function of z in a domain. So we need to prove that del square mod f of z the whole square is equal to 4 modulus f dash of z the whole square. So we know that the value for f of z is u plus iv. So see, in our left hand side we need to prove for del square modulus f of z the whole square. So take modulus for f of z, we get root u square plus v square. So square on both sides, we get mod f of z the whole square equal to u square plus v square. So multiply this with del square. Similarly on the right side, multiply with del square. Next multiply this del square inside the bracket, we get del square u square plus del square v square. So mark this as first equation. So in this we need to prove for del square u square and also for del square v square. So first we are taking del square u square. So we know the value for del square, that is Laplace operator value is del square by x square plus del square by 2y square into u square. Multiply this u square inside the bracket, we get 2 square by 2x square u square plus 2 square divided by y square into u square. Mark this as second equation. In this also we need to prove for both the terms. So first we take the first term. So we can split this 2 square by 2x square as 2 by 2x into 2u by 2x. So that is 2u by 2x. So we get differentiate this with respect to x, we get the value and simplify it, 2u into 2 square u divided by 2x square plus 2 into 2u by 2x the whole square. Similarly we are proving for the function differentiate u square with respect to y, we get 2u into 2 square u by 2y square plus 2 into 2u by 2y the whole square. So we need to add both the term and substitute in the second equation. So we get 2 into 2u by 2x the whole square plus 2u divided by 2y the whole square. So if we simplify it, we get the answer 2ux the whole square plus 2uy whole square. Similarly, we can easily say that del square into v square will become 2vx the whole square plus 2vy square. Now we have to add both the thing and from equation 1, del square modulus f of z the whole square will become, so in the 4 terms we have 2 as a common, so take it as outside. So the remaining term will become ux square plus uy square plus vx square plus vy square. So using CR equation, that is Cauchy Riemann equation, we can easily change that uy as minus vx. So change it and the answer will become ux square ux square. So that is 2ux square, and also so minus the whole square will become plus, so vx square plus vx square, that is 2vx square. So that is 2 common inside the bracket, take it as outside. So 2 into 2 will become 4 ux square plus vx square. So inside the bracket we can easily write it as modulus f dash of z the whole square. Hence we have proved that left hand side is equal to right hand side, hence we proved the equation. Next, So there is three methods given in the analytic function. And we are going to see only the third method, that is Millen-Thomson method. If only the u value is given, we use the first formula. If the v value is given, we can use the second formula. So first see, to find the f of z when u is given, that is real part is given. So we can take f of z as u plus iv, differentiate it with respect to z, we get ux plus ivx. So we can write the formula, we can change vx by minus uy by using Cauchy-Riemann equation. So the formula when u value is given, we can write f of z is equal to integral ux of z comma 0 dz minus I integral uy of z comma 0 into dz. So we have to prove the value u with respect to x and also solve for u with respect to y, and substitute z comma 0 for x and y value and substitute in this formula, we get the answer. Next, to find f of z when v value is given, similarly we change that by Cauchy-Riemann equation ux by vy, and the formula when v value is given is f of z is equal to integral vy of z comma 0 dz plus I integral vx of z comma 0 into dz plus constant. Okay, here is some problem given for the Millen-Thomson method. So our first problem is find a function w such that w equal to u plus iv is analytic if u is equal to e power x sin y. Here in our question u value is given, that is real part is given. So in Millen-Thomson method we can use the first formula, that is u value is given. So take the function as a given, so u equal to e power x sin y, differentiate it with respect to x, we get, so e power x will become same e power x into sin y. Now substitute for z comma 0, ux of z comma 0. So for x we can substitute it as z, and for y substitute as 0. So e power z into sin 0. Sin 0 value is 0. So 0 into anything is 0. So our first term will become 0. Next, differentiate this u with respect to y. So that is e power x. So sin y will become cos y. Now substitute z comma 0 for x and y. We get e power z into cos 0. Cos 0 value is 1. So 1 into e power z is e power z. So our formula for Millen-Thomson method when the u value is given is f of z is equal to integral ux of z comma 0 into dz minus I integral uy of z comma 0 into dz plus constant. We know that the first term is 0. So our second term will become minus I integral e power z dz plus constant. When integrating e power z with respect to z, we get e power z as it is. So there is minus I outside the integral. So we can write the value of f of z is equal to minus I e power z plus constant. This is how we can solve for the analytic function using Millen-Thomson method. So here is one more problem given for the real term. So we can easily say for the real value u when u is given. So take the given function u is equal to sin 2x divided by cos h2y minus cos 2x. This is in u by v method, that is v u dash minus u v dash divided by v square. Solve for it. So we get the answer 2h2y into cos 2x minus 2 into cos square 2x plus sin square 2x divided by cos h2y minus cos 2x the whole square. Now we have to substitute z comma 0 for x and y. So they change all the x value as z and the y value as 0. So substitute it, we get the value minus 1 by sin square z. Similarly we have minus 1 by sin square z can be written as cosecant square z. Similarly we solve for uy. If we substitute z comma 0, our whole term will become 0. So now we have to substitute this ux value and uy of z comma 0 value in our formula. When the u value is given, formula is f of z is equal to integral ux of z comma 0 dz minus I integral uy of z comma 0 into dz. So we know that our second term is 0, only first term will become, so minus cosecant square z into dz. When we integrate it, we get cot z plus constant. So our last question, Find an analytic function whose real part is given. Actually this is we saw for the properties of analytic function, same as it is. Real value is given. When we differentiate this u with respect to x, we get 1 by 2 into 1 by x square plus y square into 2x. 2 cancel out each other, and the remaining value is x divided by x square plus y square. When we solve for z comma 0, we get substitute x for z and y for 0, so z divided by z square plus 0. So both 1 z cancel out in both numerator and denominator, and the remaining term will become 1 by z. Similarly, we can solve for uy, that is y divided by x square plus y square. When we substitute z comma 0, that is for x and y, we get a whole value as 0. Substitute in the formula. When u value is given, our second term will become 0 because uy of z comma 0 is 0. So first term will remain the same, that is integral 1 by z into dz. We already know that when we differentiate log z, we get 1 by z. When we integrate 1 by z dz, we get log z plus constant. In this we need also to find its conjugate, that is u value is given, its conjugate is v. So we know f of z equal to log of, substitute z as r e power I theta. So log ab is nothing but log a plus log b, so log r plus log e power I theta. So f of z value is u plus iv. So log and exponential cancel out each other, so remaining will become I theta. We already know tan theta is equal to y by x. When we solve for we need to prove the conjugate, that is v term. So in left and right hand side, compare both the imaginary term, that is v is equal to theta. So theta value is nothing but tan inverse of y by x. Here is one more question given. So regular function whose imaginary part is given. Here we saw 3 problem in Millen-Thomson method in real part. So here is for last sum, we are going to see it in imaginary part. So we can take it as v, solve it for vx and substitute z comma 0 for x and y, we get an answer. And similarly solve this v with respect to y and substitute z comma 0 for x and y, we get 0. So when the v value is given, our Millen-Thomson formula is f of z is equal to integral vy of z comma 0 dz plus I integral vx of z comma 0 into dz. In our problem, we saw that vy value is 0, only vx value remains, that is plus I integral e power z minus z e power minus z into dz plus constant. So integration is common for both the term, so substitute it and solve it, we get the answer I z e power minus z plus constant. This is how we can solve the given question on the real part and the imaginary part in Millen-Thomson method by using the formula when u is given and also when v is given. Thank you all.